This is the Buck Scientific installation and basic operations videotape for the model 211 atomic absorption spectrophotometer. Upon receipt of your instrument from Buck Scientific, open the boxes and unpack the instrument, all the parts and supplies that may have been ordered with it, such as the gas regulators, hood and vent kit, or other components for doing analyses. The Buck Scientific installation kit includes all the tubing for the gas connections, electrical cords for the power supply, spare O-rings for the burner head and bung plug of the spray chamber, and the tools for making the installation or for changing any of the components. Please unpack this bag carefully, as many of the small components can be easily lost. As you prepare the instrument for installation, you will connect the power cord to the appropriate electrical outlet. You will swage the gas lines for air, acetylene, and nitrous oxide if used. This is a particular brand of gas-tight metal fitting to assure you leak-free operation of your AA system. Attach the safety drain assembly and connect the electrical interface line for the drain bottle, and insert the hollow cathode lamp and optimize for your analysis. You will plug the appropriate electrical plug into the back of the instrument, and be sure to check the little red switch to set either 110 or 220 volt depending upon the country that the system is being used in. Depending upon the gases and the accessories supplied with the instrument, we will now show the proper procedure for making a gas-tight hose fitting from the back of the instrument to the appropriate gas tank regulator. To prepare a gas-tight fitting, make sure the tubing end is cut square. Insert the nut over the end of the tubing, and then the flat ferrule with the large side facing the nut, and then the cone-shaped ferrule with the large side facing the nut. Place this assembly fully into the fitting as far as possible and slide the nut with the ferrules forward. Tighten finger tight, and then using the 9/16 wrench included with the system, tighten an additional 3/4 of a turn past finger tight to allow the ferrules to grip the tubing and create a gas-tight seal. This will allow you to remove and swap the fittings without risking any leakage of gases. Repeat this for the other color-coded tubing as needed, and then leave in place while we proceed to set up for our analysis. As part of the enhanced safety features of the Model 211 AA, we include a safety drain vessel, which is a 1-liter polyethylene container that is outfitted with a cap with a float switch that will prevent gases from being turned on if enough fluid is not in the drain reservoir. To properly set this up, take another 1-liter container and fill the safety reservoir to the top of the neck. There is a drain tube in there that will allow it to siphon as it fills into appropriate receptacle. Carefully screw on the safety lid with the float switch, and once this is assembled, have an appropriate reservoir ready to receive it. The Tygon tubing goes over the nipple coming off the burner head chamber, and then there's a small 2-electrode plug which will be connected to allow the electrical continuity to show the safety vessel has been filled. This electrical connection is important, and make sure it is secure. We can now put the bottom of the reservoir into a safety vessel to hold the overflow from the waste. In addition to the safety drain, there's a variety of other features for safe operation of the Buck Model 211 AA. The first one is the burner sensor light. This will show red if a burner head is not installed because of the electrical connections there, or the safety drain is not connected or properly filled with water. The second one is the gas pressure light. This will glow red if the gas pressure is coming to the instrument. The air and acetylene and the nitrous oxide are not at least the minimum required pressures to trigger the safety solenoid. The third light is the nitrous oxide interlock, and that means you must have the nitrous oxide burner head installed on the burner spray chamber and the safety plug installed. The third light is the flame sensor. This looks at the ultraviolet radiation coming from the lit flame to make sure that flammable gases are not being pumped into the laboratory environment. And the last sensor is the nitrous oxide rich fuel sensor. This is to verify that you have significant pressure and flow of acetylene gas to allow a safe switchover from an air acetylene flame to a nitrous oxide acetylene flame. We'll now proceed with the installation of a hollow cathode lamp and the software steps to set up for an analysis. As previously mentioned, the 211 has a number of very sophisticated gas pressure sensors installed in the system to ensure safe operation. The airflow should be typically no less than 60 pounds per square inch and preferably 75. The nitrous oxide should always be set at least 70 to 75 psi. The acetylene between 12 and 15 psi on the regulator. And your power should be fairly constant and stable, either 110 to 120 volt or 208 to 240 volt for international work. We must emphasize these are the minimum gas pressures that must be maintained for proper operation of the 211AA. Otherwise, the safety sensors will trigger and you will not be allowed to ignite the flame. One of the last steps before we begin our analysis is the insertion and alignment of the hollow cathode lamp specific for each element. The end of the lamp will have two electrodes and a plug with a key on it. That key will match a slot in the appropriate cap. Slide the hollow cathode lamp in just up to the collar and then rotate it so that the key and the slot line up and insert the socket on fully. Make sure the number on the end of the socket compares with the number on the top of the turret, as it is possible to confuse the rat tail connectors with the lamp position. Close the safety lid, and now we will proceed to go through the software of the 211AA to set up for an analysis. Once all of the hardware has been set up, we will now select the file for an appropriate element and then peek in the correct wavelength for that element. Based on the alignment of the wavelength, we will run standards to create a calibration curve. After we establish a satisfactory calibration curve, we will run the samples to get our sample values. And then we have appropriate shutdown procedures to make sure the instrument is ready the next time it is fired up for operation. There is a library of stored methods for all the elements that are capable of being analyzed by flame and furnace atomic absorption. To begin, we press the Lib key to access our library, and then using the Select key, pick the appropriate lamp number as shown in the very top line of the display so that you have the lamp position that corresponds with the hollow cathode lamp that was inserted into the socket. Using the up-down arrows, we select the appropriate element file. Furnace methods will say FURN. Hydride methods will define themselves with the word hydride. And flame methods usually have a D2 designated in the file name after the elemental symbol. Once you've loaded the correct file, press 2 and then enter to load that file into that lamp position. At this point, we can press the escape key and then follow the directions to help align the wavelength and maximize our energy, which is setting the appropriate slit and wavelength controls, which are on the right side of the instrument. Most elements are done with a 7 angstrom slit. A few are done with 2 angstrom, and the 20 angstrom slit is hardly used these days with the high energy hollow cathode lamps. Set the approximate wavelength position with the scroll based on the instructions in the alignment screen. In this case, copper is set at approximately 324.7 nanometers. We press the align key, which creates a bar graph and numerical display. Both the energy values on the screen and the bar graph depict the same information. So whether you prefer to look at a number or a picture, you will rotate the wavelength knob slowly till you get the maximum energy appearing on the screen, either the position of the bar graph or the numerical value of the hollow cathode lamp energy. It is not necessary that the bar graph be at the 0 position or anywhere else on the screen, as long as it is on the screen. If the energy happens to go off scale, you can press the align key and it will normalize the display back to the middle of the screen. One of the other optimizations is the hollow cathode lamp position based on the 2 small silver knobs under the safety lid. These adjust the positions of the lamp horizontally and vertically as marked, and as you can see, they will affect the energy coming through the optical system. If you are looking to achieve maximum sensitivity and the lowest detection limit possible, all of these parameters should be optimized to give maximum hollow cathode lamp energy in the alignment screen. Once this is done, we can press the auto 0 key to record the energy of the hollow cathode lamp, set our photomultiplier tube and deuterium background signals, and allow us to prepare for the analysis. If you should receive a background error message after pressing auto 0 or do not get a 0 absorbance, it is possible the burner is being blocked by the light beam to prevent the signal from going through. Using a business card, try and see the image of the hollow cathode lamp and the blue-purple light of the deuterium lamp, and set that so it is approximately 1/4 inch above the slot in the burner head. If the burner is set too high, as in the case of nitrous oxide operation, then the deuterium lamp beam will be blocked and you will get some errors appearing on the active analysis screen. Once this is set, press the auto 0 again and you should be able to achieve a 0 absorbance signal as seen here. With the calibration standards and samples prepared for analysis, one of the first things we need to do is check our gas flows for air acetylene operation. Press and hold the air switch and you can see from the flow meters 2 balls. The oxidant, the airflow, is fixed based on the nebulizer setting. The fuel flow can be adjusted using the fuel adjust knob located in the lower left part of the display. Usually the fuel flow is set 1 unit less than the air for a balanced flame to allow analysis of most of the elements. The options for this will be for chromium or molybdenum and tin with a rich air acetylene flame, and the procedure for this is fully documented in both the manual and the mini guide included with the system. To light the flame, we press and hold the green on button. The igniter will come out and the air acetylene flame will light. Again, a balanced flame will have a blue tongue over the top slot of the burner head